Well, thank you very much, Larry and Terry folks for hosting, and also thanks for to the ACI to give us this opportunity to really discuss a very important topic. And I do also want to commend my fellow panelists, Richard, Nathan, and Ken, for enlightening us with such good presentations. So without further ado, I know time is of the essence, and we all have other presentations, so I'll try to go as quick as possible, and I'll go ahead and start with my presentation. And the agenda for my presentation is I'm going to be talking about three things. First, I'd like to start with sharing what our Heidelberg group, as Larry mentioned, I'm with Lehigh, and Lehigh is part of the Heidelberg Cement Group in Germany. And so we have also established an approach to carbon neutrality, and I'll share some of that. I'm going to be also talking about, in general terms, what the CCS or carbon capture and storage technologies and how they've evolved so far, especially when it comes to the cement industry. And then I'm going to go into specifically talk about a little bit of our Lehigh Edmonton cement plant, which is currently undergoing a feasibility study to start a carbon capture and storage operation in Edmonton. Okay, so let's start with Heidelberg. As I mentioned, Lehigh Hanson is part of Heidelberg Cement Group, one of the worldwide market leaders in the building material sectors. We are proud to be number one in the aggregate business worldwide. We're number two in the cement and number three in the ready-mix concrete business. We have we're in over 50 countries with over 3,000 locations and over 50,000 employees. And similar to what Ken mentioned, the cement industry is heavily had the spotlight on us due to the emission reduction requirements. And obviously we recognize this and we also embrace it because we also see this as an opportunity. And that's what I like to share on this graph. This pretty much summarizes a lot of the things that you've heard so far, which is talking about the different levers of how to get to carbon neutrality. And this graph shows exactly that. It looks at the total emissions and starting in, say, 2020, and looking at different levers and how to use them. And you can see here in this graph that we have the conventional measures, which you can see examples of using PLC cements, SCMs, alternative fuels, mix optimizations, etc. So these are the existing levers that you can use. Interesting enough, you can see in this graph that the actual green aspect is going up a little bit towards the end, and it has a tendency to increase. And that's just because, if business as usual, if we don't do anything else, then just implement these conventional measures, because of the growth in the industry and the demand for more concrete in the future, that emission is going to grow. So we have, for that reason, we have a role to play here, an important role to play to make sure that we develop these technologies and use all the levers. And one thing that I'll take back from Richard's conversation here in presentation is that there's no single silver bullet here. You won't be able to achieve carbon neutrality with one or two. You need all of these levers to really come to carbon neutrality. And you can see on this graph, then you have examples like circular economy and innovative products. We have the CCS as one of the levers. We've seen in Europe a lot of cement companies talk about kiln electrification, and also the natural carbonation, which is also part of that 5 C's that we heard from the PCA roadmap. So all these combined are ways to get to carbon neutrality. So let's get into the CCS technology, which is this presentation is about. And what I like to do is start with sharing 3 types of CCS technologies. This is a slide from our Heidelberg group, which describes the 3 technologies, and it's looking at it from the point of view of deployment readiness or technology readiness level. And it's important to mention that the top 3 capturing technologies, which are the post-combustion using amines, oxy-fuel, and direct separation, are 3 technologies that are currently being developed and further assessed from the Heidelberg perspective. And the bottom three that you see there are also other technologies that help us to get to carbon neutrality. So let me start a little bit. I'll mention briefly a brief description of each, and then I'll go into the next slide, which has a video and which has a much better way of explaining it and showing exactly from the cement process how each of these technologies can be explained. So the post-combustion capture facilities refers to the separation of a CO2 from flue gas derived from combusting fossil fuels and process emissions. Post-combustion technology will be used in Norcem, Brevik, one of our cement plants, and of course our Edmonton cement plant. And the main reason being it's the most tried and true technology with a TR level of 8. Again, for those of who are not familiarized, the technology readiness level goes from 1 to 9, 1 being very early stage and 9 being commercially available. The oxy-fuel, as you can see, is not so high on the ready to deploy. However, it is an interesting industry as it involves the combustion of fuel in pure oxygen rather than air, which is predominantly nitrogen. Catch 4 is climate is the collaborative effort and R&D effort in Germany with consortium of 4 international cement players. So this is a perfect example of how industry has to come together to find a solution. This is not a company's responsibility. This is the industry's responsibility to find a solution for this. So we've come together with 4 different cement players, Heidelberg being one, Schwenk, Buzi, Unisem, and Vicat are the other ones. Lilac is the one that talks about the direct separation, and Lilac stands for low emission intensity lime and cement. And that project is one also that is based out of European Union Horizon in 2020 research and innovation. This technology addresses addresses only process emissions through direct separation. Lilac will pilot a carbon capture technology that would reduce their CO2 emissions without significant energy or capital investment. 2 projects, both hosted at Heidelberg cement plants. The first one is Lilac pilot hosted in Lexie, Belgium. And the second one second Lilac demonstration is at Hanover plant in Germany. The 3 bottom technologies that I mentioned are not directly technologies to capture industry level volumes or scales, but they do certainly help in the reduction and the carbon neutrality. And those are microalgae. We have 3 research projects executed in Sweden, Turkey, and France as well. One of the downsides to microalgae is the heavy need for the right temperature, sunlight, and intensive growth area to make this happen. Interesting enough, for every ton of algae grown, we can absorb 2 tons of CO2. So it certainly speaks to CO2 absorption, but unfortunately it requires a lot of scalability to achieve this. Hydrogen is obviously well known, and just recently in Hanson, UK, has become a partner in the High Net Worth West Consortium. Production, storage, and distribution of low carbon hydrogen will help to decarbonize other industries whose CO2 emissions primarily come from fossil fuels. Rebelsdale plant in the UK has started a pilot test of using carbon neutral hydrogen as fuel. Obviously, cost is one of the biggest challenges, and access to renewable energy is another one. And last but not least, the kiln electrification, as I mentioned, is also something that other plants are looking at, but it will definitely depend on each region and the electrification grid source that they would have. Okay, so without further ado, I will start a quick video here and hope that this enlightens. And it's very basic, but it does give a much better perspective of each of these 3 technologies that I just shared with you.
Reducing CO2 emissions while producing enough cement to meet demand is a global challenge. Heidelberg Cement invests in groundbreaking technologies, focuses on capturing the CO2 at the end of the conventional combustion process by installing a CO2 capturing unit. The nitrogen and carbon dioxide usually released by the process are redirected to this unit and cooled down. While the nitrogen is released, the CO2 reacts and binds with an amine liquid in the absorber. The resulting rich amine is heated up so that the solution splits up again into CO2 and amine liquid. The CO2 obtained is about 99% pure. It's directed into a compressor to be transported away. A second technology to capture CO2 in cement production is the oxy-fuel combustion technology, a process in which combustion occurs in an oxygen-enriched environment. In this procedure, there's a first step where pure oxygen is added to the process instead of air to improve the combustion. The exhaust gases are recirculated to the burner. The second step is at the end of the process, where the gases are redirected to the CO2 capturing unit. They pass through a first compression stage. Sulfur and nitrogen oxides are removed. Moisture is removed by condensation to avoid corrosion. The physical separation of the remaining gases displaces the nitrogen, and the share of CO2 rises up to 90%. A third technology is the direct separation, in which a special reactor replaces the conventional cyclone heat exchanger. For the direct separation process, the limestone is slowly poured into this high-temperature reactor, which is heated to about 1,000 degrees. It immediately splits into lime powder and carbon dioxide. The separated CO2 is not mixed with the flue gas of the combustion process and is therefore more than 95% pure. This means it can be captured and used right after the cooling process. But what happens to this captured CO2 which does not get emitted into the atmosphere? Well, it could be used in many ways: to produce chemicals, enhance plant growth, be transformed into synthetic fuels, or embedded in new concrete, or used to carbonate recycled concrete. CO2 could also be safely stored offshore or onshore. Heidelberg Cement, continuing to reduce our impact on air, land, and water.
Anyway, so and for those who want to see the video again, this is accessible in YouTube, and the YouTube link will also be in the presentation on the PDF. So you're welcome to see it as many times as you like. Which is moving on this presentation. One of the things that this table does now is looks at all these three technologies, and we've recognized that not one single one is perfect. They all have pros and cons. The one that we have adopted in Edmonton, and the reason why we adopted in Edmonton, is the post-combustion using amine solutions, which is shows the highest technology ready levels, and has the most benefits compared to the other ones. Not to say that the other ones are not going to be successful. It's just that in terms of ready for deployment, the post-combustion amine is the one that we are looking at. Okay, without further ado, I'm going to jump right into the actual project at hand, which is the Lehigh Carbon Capture and Storage Edmonton. This is a rendering. As you can see, this is on the top right, you can see the plant, the cement plant. And on the bottom left corner is the actual 3D rendering of what the carbon capture and storage would look like. And this is, if I zoom into the carbon capture project, this is what it would look like. This project is certainly very unique within the CCS Heidelberg domain. And one thing I do agree with Ken, whose presentation was just finished, is that there's carbon capture technology is just starting. However, I would argue though that in the cement industry is just starting, but we have seen other industries already implement, and they're operational now for a few years. And I'll give you the perfect example is the power industry in Canada through Sask Power in the project in Boundary Dam. They've done a carbon capture and storage and using a post-combustion amine technology similar to the one that we're implementing. And it's capturing close to 1 million tons of CO2 per year. And it's been working now for a few years successfully. So the technology is there, although not necessarily in the cement industry, but there's a lot of lessons learned. And that's one of the reasons why we have partnered with the International Knowledge Center, who is a group that has been created from that project to make sure that we are engaging and involving people that have been in the design process, in the construction process, and on the operation process. A few things that I can speak to the Edmonton project, which show its uniqueness. Within the Heidelberg world, this is the first that will be a full scale. The other projects that have been started, like Brevik and such, are not necessarily full scale. Ours in Edmonton will be full scale. The other one is the ability and accessibility to safe local storage. We are privileged to be in Alberta, in the prairies, where there is a lot of deep saline aquifers availability and pore space available to do the sequestration. We're going to be doing fast tracking. We're going to be, we've just completed the feasibility study and well into some initial portions of the FEED, which will need, and FEED stands for front-end engineering and design, which will need to come to a full project approval and construction. The reduction of scope 3 emissions, and sometimes we forget about, we so focus on the operational emissions, that this is really going to impact the embodied carbon in the built environment. So this will help all of our customers through this concrete supply chain reduce their emissions to be able to bring to the built environment a much lower embodied carbon. And obviously the fact that we could be using biofuel, it gives us the opportunity to perhaps be able to come closer to carbon neutral because of the use of alternate fuels and biofuel. Okay, and one of the things, that's one of the learnings we had from our feasibility study, which we'll be exploring further in the FEED, is the use of these biofuels, and which can potentially create a potential for negative emissions, quite frankly. So this is a rendering that we've created to show in a simple way the process that you've seen now, but not only to stop at the carbon capture operation or the sequestration, which you've seen, but also look at the carbon value chain, the carbon capture value chain, which is once the CO2 has been captured and secured safely and permanently, then there's environmental attributes that are generated. And those environmental attributes can come through carbon offsets or emission performance credits. But also on the cement side, we have an output. Now we would have a carbon neutral cement. And that carbon neutral cement could be the one to feed and serve the concrete industry to make carbon neutral concrete, and obviously to feed into the reduction of embodied carbon emissions in the built environment I was alluding to just recently with reduction of scope 3 emissions. This graph really summarizes what we have all been discussing here around this call for the last hour and a half in terms of the ability to reach carbon neutrality. It illustrates the different levers that are available to reduce the emission intensity of cement, but also aligns with a carbon capture and storage trajectory for our Edmonton cement plant. Let's start from the left. On the left, you have the composition of cement, which is clinker and clinker substitution. As we saw, there's fly ash, slag, or ground limestone to be used there. If we look at the baseline on the first bar, the baseline, we have the standard composition of emissions, which is fuel, 1/3, and calcination, 2/3. When we start moving into using greater clinker substitutions, like the likes of slag, fly ash, etc., we see the emission trend dropping substantially. The use of biofuels in replacement of fossil fuels will also reduce the trend. But also, as you can see here, there's a sudden jump up, and that's because the carbon capture and storage process is energy intensive and does bring the emissions slightly up, but then it captures all of the emissions. And it's important to know that that is one of the reasons why we need to have all levers and not just one lever. Carbon capture and storage alone will not allow us to reach carbon neutrality. And for that reason, If I were to put in the magnitude of the reduction from carbon capture on the initial bar, where we didn't have the other levers, you can see that we are short of reaching carbon neutral. That's just the message that I want to leave you with. It's not a silver bullet. Carbon capture and storage is not the be-all and end-all. It's an important lever to use because it will ultimately help us get to carbon neutrality. It's important to talk about a little bit on the sequestration or storage component, because quite frankly, carbon capture and storage will not give you any environmental attribute if you don't securely, safely, and permanently get rid of the CO2 through storage, for example. So I thought it was critical to look at the sequestration map here that was shown, which shows emitters in this map in North America, and also shows in blue and light blue the location of the and availability of deep saline storage throughout North America. As you can see, Alberta here is outlined, and you can see that Edmonton, which is the star, is right in the middle of the deep saline aquifers where we are located, so it gives us an opportunity to use them. And you might ask yourself, how safe is sequestration? In fact, it's quite safe, and data proves it. Over a decade of historical data used by other projects, again, not necessarily in the cement industry, but in other industries like Shell Quest, Boundary Dam, which I just referred to. The other projects are Northwest Redwater Partnership, which is a refinery, and Nutrients Redwater Fertilizer Facility, which are both using the longest and available trunk line, CO2 trunk line built in Alberta, and that's called the Alberta Carbon Trunk Line. Okay, so one of the things that we also said, and a lot of people include in the acronym, and we talk about CCS, but we also talk about CCUS, and the U in the CCUS is utilization. I didn't go too much in depth in utilization because we believe it's a matter of scalability. And this is exactly a model that we've created to show and look at all the utilization opportunities that we've had to look at and available currently in the market, and see if we can assess them to see if we could use them with our CO2. As you can see, the two axes, one is ease of implementation and the other one's revenue potential, were reviewed, and the ease of implementation carried three criteria. One was scalability, which is the major one, the most important one in my mind, because you have in our Edmonton plant around somewhere around 3,500 tons of CO2 emitted per day. And if you want to capture that amount, you really need to make sure that you have a utilization that can take it all. So that's why right now we're focusing on sequestration, which is the only solution in utilization that can allow us to take all the CO2 at once. Accessibility and deployment readiness is also key, and it was part of the evaluation. The revenue potential is important, but that takes into account different regions which might have different cap and trade regulations, or in our case in Canada, where we have the output-based pricing system, which is parallel to setting a carbon price, one that has known to be increasing substantially in the future to the tune of $170 Canadian dollars per ton in the year of 2030. So there's certainly a lot of incentives for us to be doing this, but I just wanted to show you this model, which shows that we've looked at all the other opportunities, and we might look at smaller opportunities in terms of scale, but at this point, sequestration is the one that makes sense. Last but not least, I want to leave you with an idea of where we stand in terms of the project. The project at hand typically, takes anywhere from 4 to 6 years. We have completed the feasibility and we'll start the FEED study here shortly. But as I mentioned, we're going to be fast tracking in a way that we can overlap FEED and deployment so that we can be operational by in 2026. So that's our goal, is to be operational in the year 2026.